So here is, like we saw just before, is the normal distribution curve. And here in this image we see here on the right hand side of the screen, there is a mean included, which would be the mean of all the results that are gathered in the experiment, in the test, whatever you're doing. And here we also see the percentages, 68.3, 95.4, 99.7. And then we've also got 1 and then a weird symbol, and this weird symbol means sigma. So you've got 1 sigma either side, 2 sigma either side, and 3 sigma either side, even though this one over here is being cut off slightly. So what these percentages mean is 68.3 of all the results will be 1 sigma either side of the mean, like in this little area here, from this sigma line to this one. And then here, this kind of dotted line is the mean. 95.4% of all the results then would be within this much larger area of the 2 sigma. And then 99.7, so almost all the results will be within this, in these two lines here. What you might better know these symbols are, or as, is the standard deviation symbol. So this would be 1 standard deviation instead of 1 sigma. Sigma is older term, like the original term used for it, which is what the actual symbol is. But in this case, this is the standard deviation. Then you got the 2 standard deviations and then 3 standard deviations. So also, what I also want to mention is if it's on the right hand side of the mean, so further this way, then this is plus 1 standard deviation, plus 2 standard deviation, plus 3 standard deviation, whereas this is minus 1 standard deviation from the mean, minus 2 standard deviations from the mean, minus 3 standard deviations from the mean. Now it's box plots. So basically, if we go over to here onto this box plot we've got here, we see the numbers 13, 11.25, 8.21, 7.5, 6, and 3. So what these mean is 13 and 3. 13 is the highest or maximum value that was gathered in the test of the skinfold caliper test on the triceps. That's 13 millimeters, and the lowest that was found was 3. And then here there's the number 6. We've got the lower quartile range, and here we've got the upper quartile range, the 11.25. The 7.5 is the median number, so the middlemost number of all the results, and 8.21 would be the mean of the value, mean of all of the numbers, so all of the values added up together and then divided by the amount of values that there are. So to calculate the interquartile range, which is the upper quartile and the lower quartile, kind of like the difference between them two, is say that you had 11 numbers that you were making a box plot of. You would then add 1 to 11, which would make it 12, and then you would divide it by 4, and then that will give you the third number that you've got. So whatever your third number is, so here that would be 7.5, and then you would also go on to the, oh sorry, that would be 6, not 7.5. 7.5 is the median. It would be 6, and then the upper quartile range would be would be 3/4. So 3/4 of your total values, which would be the 9th number if you have 12. Well, here we have skewed curves. So we've got both positive and negative skews. So if the shape of the curve is asymmetrical, then your data is not naturally distributed, because as you can see, it's very kind of lopsided over to one thing, whereas with the normal distribution curve, it's very neat, and then the mean's going straight down the middle. Whereas you can see here with the faint dotted lines on both of the skewed graphs, the mean's kind of curved in some areas, and it's not a straight line going down the middle. and it is said to be positively or negative skewed, depending on, if it is this kind of lopsided shape. Positively skewed means that the longer tail of the curve points to the positive end of the scale or points to the positive end of the scale, and the scores are bunched to the left of the center. Negatively skewed, therefore, just means that the longer the tail of the longer part of the tail, of the curve points is towards the lower end or the negative end of the scale, and the scores are much more bunched to the right of the center. So here we have the mean of median and mode. So when you're calculating the median with an odd number of scores, so n would be the number of scores that you've got, you would say you had 11 scores, going back to earlier. So you had 11 scores, you would then add 1, but this time you would divide it by 2 to find the middlemost point. So you would have 12, and then it wouldn't, and then you would divide it by 2, but it wouldn't be 6. That wouldn't be your answer. It would be the 6th number, or your 6th score in the rank order. So that's a common mistake. Lots of people think, oh yeah, it must be this number, it must be 6, but in fact it's your 6th number. Mode is just the most frequent score in a data set. So you could have 1, 2, 3, 3, 4, 5, 5, 5, 6, 6, 7, 7, 8, and then so on and so forth. So the number that appears the most, so you had 3 6s, and the most of other numbers would be 2, then 6 would be the mode. There are benefits and limitations for both. Obviously, the mode doesn't tell you everything. It just tells you the most common number. It doesn't tell you if someone peaked at, say, 13 shots scored in a basketball game, or in free throws, whereas someone, like the majority of people, only got 3 or something like that. And the median, again, only tells you the middlemost score, whereas mode's the most common. The middlemost score doesn't always help, because more people could be scoring higher, and it's just so happens that the middle number isn't really representing that at all, because of course it's the middle number. It's not really a proper average of both the higher and lower scores. So with the mean, we've mentioned this before briefly. So the mean is when you add up all the values that you've got, and then you divide it by the sum, or you divide your total by the amount of values that you have. So you've got 3 values total, and then together they add up to 30. Then you would do 30 divided by 3, which would be 10. So that would be the mean. The benefits of this is it's probably the best way to calculate an average of everything. But then again, with the mean, you can't see if someone kind of like peaked really high or had a really low point in a test or something. And here we see the equation, the proper equation for the mean, and the one that we want to be looking at here is the sample mean. So you can see all the symbols here, and then just work it out for yourself if you want to pause the. Now we're on to inferential stats. So here we've got the null and alternative hypothesis first. So when you're researching some data, or you want to conduct an experiment or something, you'll have 2 hypotheses. The null hypothesis, which is the thing that states that nothing will change, no significant outcome will be found, and the alternative is saying that there will be a significant outcome that is found. And with this is, you want to be, as a researcher, you want to expect the null. Don't expect the alternative hypothesis. Always expect the null hypothesis. And if there is never a significant outcome, then you have to accept the null hypothesis, which, like I said before, states that nothing significant will happen. But if you do find significant results from the experiment that you're doing, if they genuinely are significant, then only at that point are you allowed to accept the alternative hypothesis. Alright, so here I've put which test and why, and this is referring to the image in the right hand side of the right half of the screen. So here we've got the start, and basically to start off with your experiment, to decide which test you want to be conducting, you want to first identify, are you looking at a difference in the experiment? So this could be caffeine on young female gymnasts' power output or something like that. And then from there you would want to be looking at how many factors influenced it, and because you're looking at caffeine influencing young female gymnasts, it would only be one. So same or different subjects. So are you going to be conducting the experiment on only one group of people, and you're not going to be changing it? So if you're doing the same, then you'll go on to here, which is parametric and non-parametric. So like parametric and non-parametric are normally distributed results and not normally distributed results. So if you wanted, or if you had parametric results, then you would go and use the paired t-test from this. If you had non-parametric results, then the Wilcoxon paired test. And then going back a couple of steps, if you're using different participants, then you would go onto this side, and then parametric again, then you would use t-test, non-parametric, Mann-Whitney U-test. And then going all the way back to the beginning, if you were to do a correlation experiment, then it would be a much shorter way of getting to or deciding what test you're going to be using. You would either be using, or if you have parametric results, then a Pearson's correlation, and non-parametric, then Spearman rank correlation. So here we've got the independent t-test example results. So as you can see on the left here, we've got the participant numbers, the flying start of flying sprint group A second time, and then group B's time as well. And then we've got the mean here on both of them, then the standard deviation on both as well. We've also got how to work everything out up here. And then here we've got the actual working through it. So here we've got the mean of group A and then the mean of group B, and then that is divided by the square root of all of this. And then basically what you want to go through these steps is you want to just like break it down, make it much more simple, like add everything together, minus everything, do everything that you need to, so you can actually just like go through it slowly and eventually get to your results here. So after going through all of these steps, what we end up with is 0.71 divided by 0.01381, and the result of that would be the value, or t-value, which is 6.017 for the independent t-test. And here you can see this, going back real quick, this is essentially this equation just with all of these values added in here. And then we've got the DF value here, which is 18. I know it's kind of small to read, but it says 18. So you would go down here. This also is very small. I have to apologize about that. But 18 is this value here, and I know you can't read these values here because they're way too small. But our calculated t-value, which is this number here, 6.017, that's our calculated value here, which we've put down here. And then the critical value, which is the number along from 18, which is here. And then you would just be judging off of the 0.5, which I believe is one of these two here. And then that is 2.101. So as we can tell, the calculated value is greater than the critical value. That means that there is a significant difference in this test after going through all of this.